So the smoothing effect of iterations like Gauss-Seidel makes Gauss-Seidel into the class of iterative methods called smoothers. And smoothers are important because if you can smooth a solution, then you can represent the solution error in a coarser grid. And in a coarser grid, not only you do less work, but also you converge faster, right? So this is the idea of multigrid. The multigrid has two ingredients. One ingredient is a smoother, like Gauss-Seidel. You smooth the solution error. The second ingredient is a methodology to solve what's called the error equation. The error equation is how do I solve for the solution error, right, in the coarse grid. Okay, so now let's talk about multigrid. How do they work? The idea of multigrid. So the first idea of multigrid is the smoother, and the second idea of the multigrid is how do we take advantage of the solution error, which is x minus xk, that is smooth. So you don't really know what is x minus xk, right, because you don't have x. But you know, if you know it's smooth, then you can do something really interesting. If I know that x a equal to b, then applying the matrix A to x minus xk gives me a times x, which is b, minus a times xk, right? So although we don't know what is the solution error, we actually know what is a times the solution error. A times the solution error, this guy, is what we call residual, and usually denoted by R. It's residual because it is how much we are not satisfying the equation, right? So if the residual is equal to 0, we are exactly satisfying the solution and we have solved the problem. And usually the residual is a measure of how much the iterative method has converged. If it converged to, let's say, machine precision, the residual is like 10 to the minus 18, right? If you converge to, let's say, the notion of, say, you converge to 10 to the minus 5 usually means like your solution, your residual is on the order of 10 to the minus 5. Okay, so this is the residual. And the error equation is that A times a delta x is equal to the residual. And it's called the error equation because this delta x is like the error. And if you can solve this equation, the x, this residual usually have a superscript k because it's different for every different iteration, right? As you increase your k, the residual changes. So there is a k. So x, the exact solution can be reconstructed if you have the solution at iteration k and if you have an exact solution of the error equation. In practice, what multigrid does is that it performs a few iterations to compute xk, right? And then once you have xk, you can compute the residual. And once you have the residual, and I know that my delta xk, the solution to the error equation, which is the solution error, is smooth, as we just saw from the picture, then you can try to solve this equation on the coarser grid. And on the coarser grid, I have a less work to do, right? In 2 dimensions, if I coarsen the grid by a factor of 2, the amount of work per iteration is halved. And also my convergence is faster. So the amount of work is not only halved, usually like decreased by a factor of more than, in 2 dimensions, the amount of work per iteration is actually a quarter, right? And the amount of work to converge to a certain level is actually a lot less than a quarter because the convergence rate is faster. In 3 dimensions, it's even better because as you coarsen the grid by a factor of 2, I get a factor of 8 advantage in how much work I have to do.